right. Today I want to tell you about hybrid quantum control. You know, it's been, in recent years, it's becoming clearer and clearer that quantum classical integration is going to play a very important role in quantum computing. And actually, it's becoming clearer and clearer just how deep in the quantum computing stack this quantum classical integration has to go. So beyond running hybrid quantum classical applications, of course, we have quantum error correction, but really all the way down to the very basic calibrations and optimizations that we need to run on our quantum processors, and even down to the basic subroutines that we use in order to entangle our qubits. So we're seeing this need throughout the entire quantum stack to change, to adapt the quantum circuits, or actually even sometimes the single quantum operations based on classical processing that's happening in real time. And so we call these adaptive quantum circuits. These are circuits, again, or even operations in those circuits that are adaptive in real time based on the classical processing happening in parallel. And this is all about squeezing the most out of the quantum hardware by moving some of the load to the classical hardware next to it. So today, I want to tell you how we at Quantum Machines developed this unique approach that we call hybrid quantum control that enables these adaptive quantum circuits to run efficiently and with best performance, and how we're scaling this up these days. All right, so first we need to talk about what are adaptive quantum circuits. So adaptive quantum circuits happen whenever we perform some quantum operations in our quantum chip. Then we perform some measurements. We send the results of these measurements to the classical processor. Then we perform some classical operations, classical compute operations on our classical chip. And then based on these classical processing results, we generate new quantum operations to the quantum processor. Okay? It turns out that actually many of the kind of hottest topics in quantum computing these days fall under this definition of adaptive quantum circuits. And so we've looked into this, and we found sort of two dimensions according to which we can classify the different requirements from adaptive quantum circuits. The first dimension is the type of adapticity, what it actually needs to be adaptive in those circuits. And the second one is the feedback latency, how fast those circuits can adapt. So the first dimension means that basically what kind of adapticity can we do? Do we only need to make decisions on whether or not we perform some quantum operations based on classical processing, or do we fully branch the program to different subroutines based on classical processing? Or do we need to adapt to change parameters of quantum operations? For example, what happens in variational algorithms. So we change parameters of our quantum operations based on classical processing. This is the type of adapticity. And then we have the feedback latency. We identified three different categories of requirements from adaptive quantum circuits based on the classical feedback latency that's needed. QRT, SRT, and NRT. So QRT stands for quantum real time. This means that we need to adapt the quantum operations with feedback latency that is much lower than the quantum times, the coherence times. So this happens, for example, when we prepare quantum states in an adaptive manner. For example, create large-scale entanglement using adaptive circuits. We measure some of the qubits in our processor, and based on that, we perform other operations on the same qubits or other qubits, and this, of course, has to be done faster than the qubits change their states, than the coherence times. Then we have SRT, stands for system real time. So this is actually very important because one of the major contributions to the errors in even the most performing quantum computing today are drifts of system parameters. So here you can see an example in this red curve, how a superconducting qubit frequency drifts with time. You see that it drifts and then it jumps. It's pretty bad. And this is actually one of the major sources of errors in quantum computers. But if we can adapt the parameters of our quantum circuits faster than those drift times, then we can actually flatten the curve as you can see in this blue curve down at the bottom. So this is system real-time adaptive quantum circuits. And finally, we have near real-time, NRT. This is when we want the classical time, all the communication time with the classical processor, the classical processing itself, etc., to not limit the full runtime of the entire application we're trying to run. Application, calibration, whatever quantum classical workflow we're trying to run. And actually, this is not the case today, because today, in many cases, the devices that orchestrate the quantum operations, namely the control electronics, are separated, disjoint from the classical compute resources. And they're only very loosely coupled. All right, so at Quantum Machines, this is the adaptive quantum circuits are at the heart of the company. In 2019, we launched our first product, the OPX, which marked a change of paradigm, a shift in the approach from what we call the memory-based approach to quantum control, where, again, the device that orchestrates the quantum operations and the one that orchestrates classical operations, they're disjoint, they're separated, to a different approach, the hybrid control approach, which is based on our pulse processing unit, a real full-fledged processor that orchestrates the quantum operations and the classical operations in the same device, in the same chip. The pulse processing unit, or the PPU, has the ability to generate the quantum operations, also to measure qubits, but also to change, to adapt the quantum operations based on these quantum measurements and also based on classical processing, which can happen either directly on the PPU itself, because we've integrated classical compute engines into the heart of the PPU, or in other compute resources, which I'll talk about later on when I discuss our product with NVIDIA, DGX Quantum, where we tightly integrate the control system, the PPU actually, to the NVIDIA Grace Hopper platform. Together with the PPU comes our QA programming language, which for the first time in 2019 already allowed to describe in the same code quantum and classical operations that are then run at the same, in real time from the pulse processing unit. And this is really, truly makes it a hybrid development interface. All right, so this was in 2019, and this actually worked quite nicely. We grew quite substantially with over 300 customers around the world in more than 20 countries. Our customers, we have customers that are large enterprise companies, startup companies, quantum computing companies, national labs, and academic customers. We are running the Israeli Quantum Computing Center that is funded partly by the Israeli government. We merged with Q2B, a Danish company, to provide a broader range of products. And we're working with many of the leading players in quantum computing today, whether partnering with them, working with them as customers, etc. So I want to just give you a few examples of how our customers are actually using this OPX platform to run adaptive quantum circuits. I'm going to go through this pretty quickly because we don't have a lot of time. This is the first example from Andrew Zurak, CEO of Dirac. And also a professor at UNSW. So Andrew's team actually recently demonstrated that their spin qubit devices can work at higher temperature, at above 1 Kelvin, which is very important for scaling up. We just heard from Equal 1 as well. So there is a real prospect now for spin qubit device to work at higher temperature and to scale up. But once you start working at a high temperature, it actually becomes harder to initialize your qubits. So the Dirac team had to come up with a sophisticated adaptive algorithm to initialize their qubits, and this was enabled by the OPX platform that can actually perform these adaptive quantum circuits quite easily. This is another example from Tom Dreer from Quantum Machines, running at the Israeli Quantum Computing Center, developing dynamic threshold reset protocols, again, for initializing qubits. In this case, when we discriminate the state of a qubit, we measure some analog signal, and we need to decide whether the qubit is 0 or 1. In this protocol, we're actually adapting the way that we discriminate the qubits in real time in order to purify the quantum state to initialize the quantum state with a higher fidelity. These were two quantum real-time examples. Now this is a system real-time example. We're already seeing the example from Quantware, where the frequency drifts. On the right side of the screen, you can also see from the Dave Schuster's lab in University of Chicago, what happens, if you don't use this adaptive retuning of your qubit parameters. You see these wiggly lines in a qubit coherence measurement. Actually, these drifts destroy the apparent coherence of the qubits. But when you turn on the adaptive protocols, you can actually retune your qubits and actually restore the coherence, which is really cool. All right, this is a near real-time example from Alice and Bob. Alice and Bob, to characterize their qubits, their cat qubits, they run these so-called Wigner tomographies. These are the 2D plots, 2D graphs that you see in the middle of the figure there. And these have to scan some axes, some parameters of quantum operations with quite a high resolution. And if you have these memory-based controllers, it just takes forever. Again, because most of the time is spent on communicating with the classical processing devices. But with the adaptive approach, with the hybrid control approach, this can be done quite easily and very fast. All right, finally, I want to tell you a little bit about our work with Google. We partner with Google. So, Google has one of the best quantum computers, if not the best quantum computer on Earth. And they can run these quantum circuits very efficiently with very high fidelity. But what we did in this project, we added a feature to the Google quantum stack. We added the ability to perform mid-circuit measurements, meaning measurements that are done in the middle of the circuits, not at the end of the circuit, based on those, and then do some classical processing with those mid-circuit measurement results, and based on that, make decisions whether we perform some quantum operations or whether we don't perform those quantum operations. So this is now enabled on the Google chip, so-called mid-circuit based feed-forward operations. And we've actually done that in a very general way. We've integrated this into Circ. This is a capability that today is only available internally at Google. We hope that this will also change. And we've already demonstrated some pretty sophisticated state preparation, adaptive state preparation, GG state with 36 qubits that actually beats the kind of standard way of doing it, which is not adaptive. All right, but we want to do more. We want to scale this up now. So if in 2019, we brought the hybrid quantum approach to quantum control with the OPX, in 2023, we brought this approach to a new level of scale with the OPX 1000. So scaling up the control electronics has a few different aspects. First, you simply need to scale the system, allow the control system to be able to connect to and control many, many qubits. Then you need to keep the analog specifications of the control system, even at this massive scale. And finally, because we're working on the hybrid quantum classical approach, to also scale up the quantum classical integration. So OPX 1000 is in fact the highest channel density controller in the market, meaning that it has the number of qubits you can control with a single rack is the highest in the market today, with about 1,000 channels in a single unit rack, in a single full rack. And all of these different control units can actually be connected together and synchronized to very high precision using patented technology, which allows us to work on this full control system as a single controller. Here are some examples of how this would allow to control a 1,000 qubit system. This is for a superconducting qubit system. You would need about 2 to 3 racks. For a spin qubit system, you need between 3 to 4 racks. Here is for neutral atoms-based system, about half a rack, and so on. We've actually started deploying OPX 1000, some large-scale deployments. Here's an example with Alice and Bob, and many of our customers and partners. We've also deployed this in the Israeli Quantum Computing Center, where we are hosting some quantum devices, as well as the NVIDIA DGX Quantum. And we actually want to go beyond 1,000 qubits. Recently published a paper with many of our collaborators and partners, Colab, John Martinez, HPE, and many others, of how we can scale up these quantum computers even to the hundreds of thousands of qubits and beyond. All right, analog specs. I won't have time to go into this complicated topic. I see that I have very little time left. But I'm just going to say that, so just like many of the system parameters can drift, as we discussed, also the control electronics parameters themselves can drift. Here we see an example of phase drift. And if the phase drifts in certain schemes, or if other parameters of the control system drift beyond the threshold, for example, of quantum error correction, we're kind of screwed. So we need to build systems that have this very high stability of the control electronics. But we can even do better than this if we use this adaptive approach, this hybrid control approach. Then we can use the ability of the controller to actually change the parameters in real time to measure the fidelities on the qubits, in situ on the qubits, and then retune even the control electronics specs themselves. And we've done some demonstrations of this. This is an example of how you flatten the phase stability curve. All right. Finally, in the little time I have, I want to tell you about how we're scaling up the quantum classical integration. So about 2 years ago, we partnered with NVIDIA because we shared the vision of doing that exactly. So NVIDIA is making the best high-performance compute systems, and we believe we make the best quantum control systems, and we need to couple them now. So the pulse processing unit has its own classical compute power, but we want to scale this up massively if we want to go to tens of thousands of qubits and beyond. And so we've created a very low latency interface between the OPX 1000 and the Grace Hopper system, which allows to seamlessly, integrate and run programs in QA and CUDA and CUDA Quantum to perform these quantum classical workflows. We've just started using this system, doing some first demonstrations with the system in the Israeli Quantum Computing Center. We run on some QPUs, and we run some reinforcement learning agents, just kind of off the shelf that we took from OpenAI, open source platform, and this actually works. So this is an example from running this kind of adaptive circuits on using reinforcement learning agents running on the GPU, on the Rigetti chip in the Israeli Quantum Computing Center. All right, so I think with that, I'll stop here and I'll take some questions. Thank you.